Okay, I think we are going to start in a few seconds.
Oh, it managed to unmute it. Can you hear me?
Yes, I can hear you now. Can you hear me?
Yes, very clearly.
Okay, that's very good. So then I think it's time to start now. So hello, guys. Welcome, and thank you for attending this first lecture of our course on heterogeneous systems. The entire title of this course is Programming Heterogeneous Computing Systems with GPUs and Other Accelerators, and that's what we are going to learn in this course, how to work with heterogeneous computing systems, especially and with a special focus on GPUs and parallel programming. Basically today what we are going to do is just introducing the main goals of the course. We will give also a little bit of background on heterogeneous systems, recent interesting devices that are used for different purposes. For example, ML and neural network accelerators that we will briefly mention over the course of this first lecture. Starting from next Friday, we will have more in-depth lectures about architecture of SIMD processors, GPUs, GPU programming, parallel patterns, etc. I will show you some materials later for your reference, because you can already check what is going to be more or less the different collection of the collection of different lectures that we are going to have in this course. You can already check them in the website of the past semester. Feel free to stop me anytime. I will eventually ask you as well if you have any questions, and also feel free to use the chat here in Zoom. If you are attending the lecture in YouTube, you can also use the YouTube chat. I will keep an eye on it in case that there are any questions there. So before we go into details about the course, I think it's good to take a look at the contents of the course catalog with respect to this course, because there is where the objective of this course is clearly defined, I would say. This is the description, or this is the objective, the description of the objectives of this course. Motivate with the difficulty of scaling performance and efficiency of CPUs. And this is something that affects many modern important workloads, such as machine learning and artificial intelligence, but also other domains such as bioinformatics, machine learning, graph processing, medical imaging, personalized medicine, etc. So there is a need for heterogeneous devices, and good examples of other devices other than CPUs that we can find in computing systems these days are graphics processing units, FPGAs, also specialized accelerators, for example, the tensor processing units that are used for neural network training and inference, and even more newer trends such as near data processing architectures. Even though there have been great advances in the adoption of heterogeneous systems in the recent years, there are still many challenges to tackle. And that's what we are going to try to do in this course, at least partly. So one possible way of starting the discussion about these different heterogeneous systems is to take a look at the Flynn's taxonomy of computers. Back in 1966, Mike Flynn already proposed a classification of computers where he divides into four main groups, depending on how the devices operate on the data. The first of the example is SISD, single instruction, single data, where a single instruction operates on a single data element. This is like a sequential processor, same as we can have in very simple CPUs with just one core. SIMD is single instruction operating on multiple data. And this is where we are going to start indeed today, and also in the next lecture, discussing these devices or these architectures, SIMD architectures, where with a single stream of instructions, we compute on multiple data elements. We are going to pay special attention to this type because they are one of the basic architectures that compose graphics processing units. And as I said earlier, graphics processing unit are a key device, are going to be a key type of device in this course. The third type of computer is MISD, multiple instructions operate on single data element. It's not that easy to find good examples in the real world, but the closest form could be systolic array processors. We are going to mention them also in today's lecture and also in some other lecture later in this semester. And finally, the last one is MIMD, multiple instructions, multiple data. Multiple instructions operate on multiple data elements. So we have multiple instruction streams. Examples of these can be multiprocessors, multi-core processors, or other types of multi-thread processors. As I said, we are going to start with the example of heterogeneous processor or heterogeneous device. The example today are going to be SIMD processors. And in particular, we are going to start with the SIMD ISA extensions that we can find in multiple CPUs these days, because even though CPUs can be, multi-core CPUs can be seen as a MIMD machine or a MIMD computer, they are also heterogeneous in themselves because they have different types of processing elements. And one good example of these are the SIMD extensions. So in the single instruction multiple data extensions, a single instruction operates on multiple pieces of data at once. This is useful in many different applications, for example, processing of graphics, but many more, as we will see and we'll discuss in this lecture and over the entire course. And the basic idea in these SIMD extensions is to perform short arithmetic operations on multiple elements at the same time. For example, we can add 4 8-bit numbers with a single instruction. The basic idea would be to start using one conventional register, 32-bit register, for example, as we can have in any CPU, and divide this register into 4 parts of 8-bit each. The basic idea to be able to compute 4 additions at the same time would be to modify the ALU to eliminate carries between 8-bit values. For example, the carry out of this bit 7 won't be propagated to the carrying of this bit 8. And this way, we would be operating on 4 elements at the same time without any interference between the 4 additions. So that's the basic idea in the SIMD ISA extensions that we can find in CPUs. And a good example, and actually a seminal example of these, are the Intel Pentium MMX operations that were already implemented in the 90s. The idea, SIMD, is operate one single instruction operating on multiple data elements with graphics in mind. When these MMX instructions were proposed and first implemented in the 90s, as I said, they had multimedia and graphics operations in mind. And these MMX extensions provide different ways of operating on 64 bits. If you have a 64-bit register, you can divide it. Well, you can just operate on 64-bit elements on a 64-bit quad word, or you can divide it into 2 parts and operate on 32-bit double words, or on 4 16-bit words, or on 8 8-bit bytes. So it all depends on how you create connections between the carry out and the carrying of the next bit, and where that carry stops in order to keep the different operations independent. I want to give you an example of how to use MMX instructions. This way, you can just see one first example of how to operate with a SIMD machine with a parallel architecture. In this example, what we are going to do is to overlay the human in one image on top of the background in another image. So here we have two images, X and Y. As you can see, on the left-hand side, we have the image of a woman on a blue background. And what we want to do is replacing the blue background with a blossom background so that the new image is going to look like this on the right-hand side. Performing this operation on a sequential CPU is pretty straightforward. We just need to go one by one over all the pixels of the input image of the image X and check if the corresponding pixel is blue or not. If it's blue, then we are going to replace the pixel in the new image with the corresponding pixel of image Y, which is the blossom background, as you see. If it's not blue, that means that the pixel belongs to the woman, to the image of the woman. So what we do is just copying the pixel from the woman to the final image, this new image that we have here on the right. Because all the computations that we are performing here are exactly the same for all pixels, that means that we can operate on multiple pixels in parallel, just with a single instruction or with a single stream of instructions. So what we can do with the MMX extensions is to check several pixels at the same time, whether they are blue or not. To do so, we compare to an array or a register that contains many bytes, each of them with the value or with the color blue, and we are going to compare one by one these pixels here to generate a bit mask that we are going to use later to filter the filter out the elements from the image X and the image Y that we really need to copy, really need to transfer to the new image. And that's what we do in this part here. After having generated this mask that is stored in this MM1, we can filter out those elements of the blossom image that could be where the image of the woman herself is. And we filter out those that we don't need, and we only keep those that we really need, that are those in the that will appear in the background. And we do the same for the woman's image. We filter out all the blue pixels, and we just maintain the pixels that correspond to the woman's image. After that, we combine the filtered pixels from both original images, and then we obtain pixels from the final image, this new image that contains the woman in front of the blossom background. So this is more or less how a SIMD machine would work. You can operate on multiple elements at the same time using a single instruction. But this is just an example of the heterogeneity that we can find in current computing systems. As I said, it's very common to find SIMD extensions in CPUs, in multi-core CPUs, but even in the same system on a chip, you can also find other devices like specialized accelerators, neural network accelerators, for example, or GPUs, or maybe even reconfigurable logic, like, for example, FPGAs. And it's more and more frequent as well that we find ways of performing coherent communication across these different devices with a specialized coherent interfaces or coherent interconnects that allow these different types of devices to have coherent copies of data. Let's say the most recent values for the data that they need to use, regardless of what device is modifying them. So all of that will be covered with more or less detail in this course, but for sure, we will talk about all these different components because they are important in current heterogeneous computing systems. So goals of this course First of all, we are going to introduce the need for heterogeneity in current computing systems in order to achieve high performance and energy efficiency. You're going to get familiar with some of the different heterogeneous devices that are available in computing systems. You're going to learn parallel programming, and we will focus on GPU programming with CUDA or with OpenCL. But even though we will mainly target a specific architecture and a specific type of device, the most learnings that you will have about parallel computing patterns in this course are applicable to all parallel machines or to many parallel machines. And we will in fact mention other examples when we are discussing and presenting the parallel patterns. You are going to learn as well how to do workload distribution and parallelization strategies. These are the parallel patterns that I was mentioning, and you will work hands-on because this is a projects and seminar course. So here the goal is that each of you develop your own hands-on project. And there might be many different things like programming heterogeneous architectures, analyzing workloads, proposing scheduling, offloading mechanisms, etc. These are just, like, let's say, different potential directions for the projects. By the way, I will mention that later as well, but we are going to discuss the projects in the next lecture. We find heterogeneity in many different levels. We have already seen a picture with an entire system on a chip with 3 different types of devices: CPU, GPU, FPGA. But even if we go in and look inside each of these devices independently, like for example, a GPU, we will see that there is also heterogeneity inside. For example, this is the layout. This is the big picture of an NVIDIA A100 GPU with 108 cores and 40 megabytes of L2 cache. If you look at all these cores here in the image, you see that they are more or less homogeneous, right? But if you go inside them, you'll see that they have different execution units for example, different data types: integer, floating point, double precision. And we also find this area here, the tensor cores, that are small cores that are specialized for machine learning and deep learning. And they appeared first in the Volta architecture back in 2017, and since then they have evolved this generation of A100 GPUs, integrated new support for sparsity, where they can filter 0 entries and compress and operate on compressed matrix tiles, and this way be more efficient, because as you can imagine, if you are performing multiplications with 0 entries, that result is going to be 0, so we are just wasting energy. We don't need to perform that multiplication, right? And that's something that it's more and more common in neural networks these days. Sparsity is more and more common in neural networks these days, and that's why these specialized units start support some sort of sparsity in order to make compression and then computation more efficient. In summary, what I wanted to say is that we see heterogeneity even inside the core of one specific heterogeneous device. This is a more recent GPU. This is the H100 GPU that was presented in 2022. They keep including innovations inside the tensor cores. In the 4th generation, they also see more heterogeneity in the data types that are supported. These tensor cores support floating point, 32-bit floating point operands, 16-bit floating point operands in 2 different formats, and also 2 different formats of 8-bit floating point values. These tensor cores are specialized for machine learning, training and inference, neural networks, or deep learning, but they are also not the only devices that have been, or in this case, execution units in one specific device that have been designed for neural networks and for deep learning. I think another really interesting device is the Cerebrus wafer scale engine. Is the largest ML accelerator chip, because in reality it's not one single chip, is an entire wafer, as you can see in the picture, and you can compare it as well with the size of one of the largest NVIDIA GPUs, in this case, the NVIDIA Titan 5. You can see the difference in the number of transistors and also the entire area. This picture here corresponds to the wafer scale engine from 2019. 2 years later, they announced an even larger one with basically twice the number of cores, twice the number of transistors, and also much larger than the largest GPU at that time, that is the NVIDIA A100. This was around 2021, as you see. This is a very interesting device, very exciting direction in the design of machine learning accelerators. And if you're curious about the Cerebrus wafer scale engine, I can recommend you this talk, this Safari Live seminar that Sean Lee, one of the founders of Cerebrus, delivered last year in our group. And another very good example of accelerator design for neural network training, inference, machine learning, and artificial intelligence. Pretty prime example are the tensor processing units that were first proposed or were first developed by Google back in 2016, 2017. As you can see here on the right-hand side, this is basically a systolic array. Remember that we mentioned systolic array in the beginning of the lecture as an example of MISD machine. Here what we have is a flow of data coming from the left, for example, images or input feature maps. And what the systolic array basically does is performing a matrix multiplication, multiplying and accumulate in these accumulators here at the output. Why matrix multiplication? Because matrix multiplication is a key primitive for neural networks and many machine learning and artificial intelligence algorithms. We are going to talk about matrix multiplication in detail in this course and about how to lower convolutions into matrix multiplications, which is a very common technique in training and inference of neural networks these days. And this is why this operation is so important and why there are units that are specialized for this specific operation, units and entire accelerators. That was the first generation of the Google TPU. The second generation, 1 year later, they basically multiplied the total, well, the number of chips by 4. This also increases the flops, the floating point operations per second, very significantly. They also replaced the DDR3 memory with high bandwidth memory in order to have a higher bandwidth of access to data, in order to be able to feed these fast systolic arrays with data coming from memory. And the TPUs keep improving over time. The third generation increases the number of matrix units of systolic arrays from 2 to 4 per chip. This here on the left is the version 2. This one on the right is the version 3. Again, they are doubling the teraflops per chip as well. And in the fourth generation, even a higher jump from 90 teraflops to 250 teraflops per chip in 2021. The goals supporting new ML applications, such as computer vision and natural language processing, recommender systems, reinforcement learning, etc. And this is again the picture of the modern systolic array that I mentioned earlier, or that we have seen earlier. And here you can see a little bit more detail of this systolic array, this matrix multiply unit. Observe how we have an input coming from the left, this systolic data setup that is feeding input feature maps that might be coming from somewhere else, from external memory, and also the weights coming from this DDR3 chips or HBM memory, the weights of the neural network coming from here, performing the matrix multiplication and accumulating the results in these accumulator registers. So just another example of a heterogeneous device. And as I said earlier, we may have heterogeneity even inside the same chip. I gave you the example of GPU cores, but here you can see another really nice example, the Xilinx Versal ACAP that has three types of compute engines inside the same chip. It has scalar processors like regular CPUs. They have adaptable hardware that, as you'll see, is similar to it's like an FPGA, right? And they are designed for latency critical workloads, while the Versal ACAP also integrates some vector processing units, like SIMD units that are specialized for signal processing, video and image processing, and other parallel workloads. Neural networks and machine learning can also be good examples for those vector engines, or here in this figure called intelligent engines, or AIE, artificial intelligence engines that are basically vector processors. But as you see, very interesting picture here with the three compute engines, scalar cores on one side, in fact, two different types of dual core ARM CPUs, adaptable engines in the middle, an FPGA where you can have your custom memory hierarchy with the different SRAM-based memories that FPGAs can have, and on the right-hand side, the intelligent engines that are like vector or SIMD units with more specialized for more parallel and regular workloads. Okay, do you guys have any questions so far? Okay, I can continue and we can clarify anything that might be needed later. Okay, we were talking about different types of devices. Many of these devices and accelerators are specialized for important workloads. Important workloads these days are machine learning, artificial intelligence, neural networks. Another interesting example of such an accelerator, such a processor, is the Groq tensor streaming processor, presented in 2020. Here, as you see, it's designed for machine learning workloads that exhibit abundant parallelism. The good thing with machine learning, or at least many of machine learning workloads, is that they have quite regular structure, so it's relatively easy to create. Well, relatively easy. It must not be easy, but at least it's possible to create a deterministic processor with a producer-consumer stream programming model. If you are performing matrix multiplications, you are performing dot product operations, you know what's the exact sequence of operations that need to happen for that matrix multiplication to be executed, right? It's different from other workloads where you may have irregular memory accesses or indirect accesses that require you to first go to memory, fetch some pointer, and then depending on where these pointer points go again to memory and bring another value, etc. That's what happens where we have more indirect access pattern, more irregular behavior. If you think about the matrix multiplication, we are accessing rows, we are accessing columns of matrices. So the computation and the accesses to memory and the operations that we need to perform at any given point are quite predictable. That's why Groq designed a deterministic processor where they can orchestrate the flow of data over all different units that the Groq system integrates. And here you can see already a pictorial representation of these units with matrix units, similar to the systolic arrays that we have mentioned earlier, switch units that are used for communication, shuffling data from the matrix unit to the memory unit. There are also vector units similar to the matrix unit, but intended to operate on a single vector. So they are more similar to a SIMD unit, and so on. These are the different units that you can see inside Groq tensor streaming processor. And actually, you can see here the die photo with these two hemispheres that the Groq processor is divided into. On the left-hand side, we see memory. We see this switching unit to move data, to shuffle data around, and we have the MMX units, the matrix multiplication units. And here in the middle, there is a vector unit for SIMD operations. You can also see like different interfaces and links for communication across chips, also for communication with another external device, for example, a host CPU via the PCI Express bus. And Groq proposes an entire hierarchy, a scale-up hierarchy from the Groq chip to the card that may contain more than one chip. And inside the one node, there will be multiple cards, and these different nodes can all be put into the same rack in order to scale out, in order to be able to train larger neural networks. I think Groq is a very interesting device as well. We may talk about it in more detail in a later lecture. For now, what I would recommend you is this Safari Live seminar that Oscar Menzer from Groq delivered basically 2 months ago in our group. The talk is accessible from the Safari website, and also you have here the link to the YouTube live stream. It's still available. And another prime example is this Tesla Dojo from 2022. Tesla obviously needs very systems, large systems to train neural networks, and they are very innovative in the design of new devices that can help in this purpose. I think it's pretty interesting, this Dojo training matrix, or this Dojo training system that is composed by different types of processors as well. Here you can see a CPU, a regular host CPU. They will also include this DIP, as we'll see, sort of an interface processor to communicate between the CPU and the tiles. These tiles probably similar to a systolic array as well, to perform matrix multiplication, matrix vector multiplications that are necessary to train to do neural network training and inference. Observe also that the different devices have different sort of memories, heterogeneous memories as well. CPU may have conventional DDR-X DRAM, while this DIP, this interface processor, has HBM memory that provides significantly higher bandwidth. And well, here you can see a picture of this Dojo interface processor with its 32 gigabytes of high bandwidth memory, a total bandwidth of 800 gigabytes per second. And this is the D1 chip, the tile itself that is used for training the neural networks. As you see, well, really high number of teraflops for different supported data types, 16-bit floating point, 8-bit floating point, 32-bit floating point, depending on what are the specific needs of the network that they're training. Okay, more examples of heterogeneous architectures. And this is actually a trend that I mentioned in the very beginning, near data processing or processing in memory. That is a trend that tries to alleviate the data movement bottleneck. And what's the data movement bottleneck? Is the frequent need for communication between memory and storage and processing elements and compute units. One problem with that, and probably all of you are familiar with the von Neumann model, where we have the processor on one side, the memory on another side, and in the middle we have a communication unit. The problem that we have in most current systems these days is that this communication unit is very narrow. So because it's very narrow, it basically behaves like a funnel. And that creates a lot of contention when accessing data, when moving data from one side to the other side. One way to alleviate this data movement bottleneck is called processing in memory. And as the name indicates, basically consists of placing processors inside the memory. And this can happen in many different ways. One nice example is this AppMem processing in DRAM engine from 2019 that basically modifies DDR4 chips. As you can see here in these DIMMs in the picture, they modify these chips to include small processors called DPUs near each DRAM bank, near each memory bank. And this way, the host CPU can offload computation to the processors here inside the pin chips, and these processors can access data locally, operate on the data in the memory arrays, and do it at much higher aggregated bandwidth, because you're going to get much more bandwidth if you have many processors operating inside these chips than if you just try to access the data through this data bus here that is, as I said, behaves like a funnel. AppMem is a French startup. It's a small company, but it's not the only company that is exploring and designing processing in memory devices. Samsung is one major DRAM vendor, announced already 2 years ago their first processing in memory architecture targeted at AI and machine learning. It's called FIMDRAM or HBM-PIM. It's based on HBM memory. What they basically did was modifying the design of the HBM2 memory layers in order to place small processors called PCUs, these PCU blocks that you can see here in the die photo, inside each every two banks of DRAM cells. These PCU blocks are small SIMD units that have higher bandwidth access to the nearby banks, and they can perform multiplications and additions pretty fast. And these multiplications and additions can be used to execute dot product operations or matrix vector multiplication or matrix-matrix multiplication that are needed, as I said, for machine learning and artificial intelligence. Samsung has other proposal, a different type of processing in memory system. In this case, is DIMM-based. What they do here is placing a small FPGA on top of the DIMM, and this FPGA will implement several processing elements that have access to high bandwidth access to these memory chips on the DIMM, and they can exploit rank level parallelism, accessing all chips at the same time, and this way increasing the overall bandwidth of the system, alleviate the data movement bottleneck in that sense, and accelerating workloads that could be memory bound in the baseline system. The example here is a recommendation system that they tested in their first prototype. But Samsung is also not the only major vendor that is exploring and designing processing in memory devices. SK Hynix is another major DRAM vendor that announced last year their GDDR6 AIM accelerator. Similar to the HBM-PIM proposal from Samsung, they also place processing units near the memory banks, and these processing units are also specialized for multiply and accumulate operations that are needed for machine learning and artificial intelligence. So these are just some examples of heterogeneous computing systems, and as I said, we are going to have many, or we potentially will have many different types of devices inside the same system on a chip or inside the same compute system. But it's important as well to find efficient ways of communicating between these different processes, the different types of processors, and also keep coherent data in their caches and in their sketchpads. Though that's the role of the coherent interconnects. Examples of that are, for example, CAPI or OpenCAPI, or the most recent CXL Compute Express link. In the traditional approach to a system with heterogeneous devices, we need to explicitly move data between the main memory of the host processor of the CPU, for example, to the accelerator, for example, an FPGA, right? That's a traditional approach, and that's what these coherent interfaces try to optimize and try to make, let's say, more seamlessly integrated and in summary, easier to use by programmers and users. So that was the proposal from first CAPI and CAPI 2 that were the first two interfaces that IBM proposed, but then OpenCAPI was a standard that was followed by several vendors and providing a coherent interconnect between different types of accelerators or different types of devices in a system. It's not only OpenCAPI, also other vendors, Intel, for example, started to integrate as well these coherent interconnects between their CPUs and their FPGAs in order to provide a unified view of memory and in order to allow tighter integration and finer grain collaboration between different devices in the system. The most recent trend and most recent standard is CXL, that this industry standard interconnect that it's being followed by many vendors these days, and it's being developed. I think CXL is right now in its 3.0 specification, and I think that there will be more to come. And it's really providing or starting to provide a very interesting range of possibilities for different devices in the system, from accelerators with memory, or simply memory buffers in order to extend the effective memory capacity of a system. There are different, indeed, 3 types of protocols supported depending on what's the sort of device and what's the type of communication that we want to have between these different components in the system, like components like a network interface card, a regular accelerator such as a GPU or an FPGA, or simply memory buffers, memory extenders that allow a host processor to have access to much larger memory. This Compute Express Link, as I said, is a really promising standard and hopefully will allow much more seamless and close integration between different devices and much more fine-grained collaboration. And in summary, more performance, more energy efficiency, and also better programmability as well. Okay, so we are going to talk about all these types of devices and interconnects more over the course of the semester. For now, let's summarize a little bit what are the goals of the course, what will be key takeaways of this course. The first one, this P&S is aimed at improving your knowledge in computer architecture and heterogeneous systems, your technical skills in programming heterogeneous architectures, for example, GPUs or FPGAs. We also have may propose projects about FPGA programming. You will develop as well your critical thinking analysis and will interact with a group of researchers that are the Safari research group. You will get familiar with key research directions in our group and basically in the landscape of heterogeneous computing systems. And finally, you will improve your technical presentations because you will present your project at the end of the semester. The key goal of the course is to learn how to take advantage of existing heterogeneous devices by programming them, analyzing workloads, proposing offloading, scheduling techniques, etc. There are not many prerequisites in this course, but you are expected to have some good background in the digital design and computer architecture. If you want a refresher on these, I can recommend you to take a look at the contents of our website, Professor Mutlu's DDCA course that is taught every spring semester. We are right now starting the spring 2023 semester, but you can find all the materials of the course in the website of the past spring semester. You are expected to have familiarity with C and C++ programming. This is important for many different potential projects like programming heterogeneous architectures, doing simulation work, etc. So we expect that you can program, and if you have also some basic knowledge on FPGA programming or GPU programming, that will be even better. For sure, what we expect from you is that you have an interest in computer architectures and computing paradigm, in discovering why things do work or do not work, and solving problems and making systems efficient and usable. This course is delivered by me, by the Safari Research Group. The Safari Research Group is led by Professor Onur Mutlu, who is a professor at ETH Zurich since 2015. He has plenty of experience in research and teaching on computer architecture, computing systems, hardware security, bioinformatics, etc. And the rest of the team is me. I'm the lead supervisor, and I will teach most of the lectures, not all, but most of the lectures of this course. There are also other supervisors. They will be possibly your supervisors in your own personal project. Dr. Mohammed Alser, Dr. Behzad Salami, and Dr. Mohammed Sadar, as well as Joel Lindegger, who is a PhD student of our group. So you can, you will have a chance to meet us and to know from us as well, but you can also take a look at the entire Safari Research Group in our website. It's a pretty large group with around 40 researchers these days. We do a lot of work in research, teaching, and also dissemination of our activities in different ways. For example, the newsletters that we publish from time to time. This is an old edition, but a new edition is coming, and hopefully will be released soon. And we also organize many other activities. I mentioned earlier a couple of Safari Lab seminars that I would recommend you. You have a link here to all the Safari seminar series that we started already in 2021. All the Safari Live seminars, you can find them in our website as well, with links to the YouTube recordings, to probably in some cases the slides as well, if you want to take a look, etc. In our group, there are we do research in many different things in computing systems, but we have a clear focus on computer architecture, hardware, software, co-design, and also bioinformatics applications. In computer architecture, we cover basically all different components of the computer architecture and the computing systems, from the persistent memory and storage to hybrid main memory, heterogeneous processor and accelerators, etc. Okay, I have this slide here for you guys to introduce yourselves, but I think that we can skip this for now. We will have a meeting next week where we will discuss the different projects, and I think that can also be a good opportunity for you to introduce yourself and also let us know what are your main interests, because probably based on that, we will find what's the perfect match in terms of hands-on project for you to develop this semester. Do you guys have any questions so far? Okay, so if there are no questions, let me continue with course requirements and expectations. Attendance is required for all meetings, but there is a lot of flexibility here. In fact, this is probably one of the few live meetings that we are going to have. As you'll see, the lectures are going to be always in this slot, Friday at 9 a.m., or most of the times at least will be in this slot, Friday at 9 a.m. But it's likely that we'll have a pre-recorded lecture that you can watch on Fridays 9 a.m. or sometime later, because the lecture is going to be for your own use. It's going to be there, available forever. So just feel free to organize your schedule, your weekly schedule, and your time in the way that you prefer. But you are expected to attend the lectures, study the learning materials, and for sure carry out your own hands-on project that, as I said, we will discuss next week. We also expect from you that you participate, ask questions, contribute thoughts and ideas, and also read relevant papers. It's important to read papers in order to understand how research works and also to get inspired on how to explore new ideas. We will help you a lot in your projects. You will have a very tight supervision from us, from me, or from one of the other supervisors in this course, and we will push for good work that may eventually get published if you really do a good job and want to and you want to publish it as well, of course. So important materials you will find in the course website. Here you can find the link, information about the course, also all materials of the course, links to the lectures, links to the slides, etc. Check also your email for announcements that we might make from time to time, either via Moodle or with direct email, as I already did until now. And remember that there is also a Q&A forum in Moodle that you can use for any questions that you may have with respect to the course, basically the course lectures, because if you have questions about your own project, you can directly discuss them with your supervisor. You will meet your supervisor or supervisors regularly. This is the link to the current website of the course, the Spring 2023 edition, and also a link to the YouTube live stream where we will have the playlist where we will have all these lectures. I already provided you with some learning materials over email. You can find them also here in this slide. They are recommended, very much recommended, of course. But yeah, but there are, for example, here some introductory lecture to SIMD processors and GPUs and to GPUs and heterogeneous programming. We are going to cover these contents in later lectures in this course as well. So I think it would be good that you watch these lectures or take a look at the slides before the lectures of this semester start or continue, so that you have already some background and that facilitates your later learning. But as I said, we will cover all these contents with quite a bit of detail this semester. In next week, meeting 2, we are going to announce the projects. I already said that. We will give you a description about these projects and you will have a chance to select the project. We will give you a couple of days to think about it and then express what are your preferences. Based on that, we will make a decision on what's the right project for you. And after that, you will start having one-to-one meeting with your supervisor or supervisors in order to start developing the project. In next meetings, I mentioned this already, we are going to have lectures about GPU programming, parallel patterns, also lectures about recent research works, and then individual meetings with your mentors. And finally, at the end of the semester, after you have developed your project, presentation of your work. For the entire view of what's going to be more or less this semester, please take a look at the website from fall 2022. There you have, as you can see on the right-hand side of this slide, links to all recordings, all slides, and also at the very bottom of the website, you'll find more recommended materials, papers, etc. Okay, so that's all about the introduction of the course. We are about to wrap up and finish today's lecture. If you have any questions right now, please guys, let me know. If not, I'm going to start introducing what will be the contents of the next lecture, lecture number 2. We will talk about exploiting data parallelism. We have already started talking about this. We started the lecture today with SIMD processors, and that's going to be the main topic of next lecture, SIMD processors and GPUs. Remember that SIMD processors are one of the 4 different types of machines that Mike Flynn identified in his 1966 paper. A SIMD machine is a machine where single instructions operate on multiple data elements at the same time. There are 2 classic examples of SIMD machines. One is the array processor, the other one is the vector processor. We are going to mention very briefly what are the key differences between these 2, and we will see that real SIMD machines, like for example GPUs, have characteristics of these 2 types of SIMD processors, array and vector processors. I already gave you the example of SIMD extensions in CPUs, the MMX example for image overlaying, the idea that we are going to perform the same computation on every single pixel of an image. And because of that, we can take advantage of that, and we can save instructions basically by having one single instruction operating on multiple data elements. And I think this example of the image overlay must already be clear. In SIMD processing, we have a single instruction operating on multiple data elements, and we say that this is either in time or in space, depending on the type of SIMD processor that we consider. We have multiple processing elements or execution units, and this operation in time or space is called the time-space duality. For example, in an array processor, one instruction operates on different multiple data elements at the same time using different spaces or different processing elements. While in a vector processor, one instruction operates on multiple data elements in consecutive time steps using the same space or the same processing element. I think this is clearly represented in this slide. Observe that on the left-hand side, you have the instruction string, 4 different instructions: load, add, multiply, and store. And each of these instructions is a vector instruction. It's one single instruction that operates on multiple data elements. But the way that you can do that is in different ways. You can have an array processor where you have multiple processing elements, and each of these processing elements is capable of performing different operations like load, add, multiply, store. And in this array processor, we have the same operation happening at the same time on different array processors, as you see. While we can also have the vector processor, where the execution units are specialized for load, add, multiply, or store. And here, with a single instruction, you can operate on multiple data elements at different times using the same space, as you see. For example, this addition here operates on 4 elements, but it does it on 4 different cycles, and all of that is happening in the same unit, this addition unit. Observe how that is different from the array processor. But if you look at the internals of an NVIDIA GPU, for example, the GPU core, you'll see that they have part of array and part of SIMD, part of array and part of vector processor. Why is that? Because we have many different units. You see specialized for int32, floating point 32, load and store, 64-bit floating point, or even these tensor cores. But we also have several of these units. So we can operate both in time and in space using individual instructions or a single instruction string. It's not easy to program, by the way, all these systems. Hopefully, in this course, we will help you to learn how to do that. But I think it's really interesting, this reflection from Fisher in 1983, where he said that to program a vector machine, or in general a SIMD machine, the compiler or the hand coder must make the data structure in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in first place and just as hard to change. So what this means is that if you have a parallel machine, such as these SIMD processors that are quite static, because basically you have a certain number of execution engines, right? And these execution engines have certain capability, but they might not be very flexible. You need to adapt your workload to the execution units that you have. So workloads might not be so regular in the real world. And even if they are regular, they may not have a size that is an exact multiple of the number of units that you have. So programming these SIMD processors in an optimal way is quite challenging sometimes. There have been a lot of progress in recent times, in recent years, on how to program these systems. And a good example of that is the CUDA programming model that we are going to cover extensively in this course, but still is not that easy to do. And that's why it's important to attend this course. So as we will see, and we'll continue discussing about this in our next lecture, in an heterogeneous system with a GPU, you will typically choose the best device for the different parts of your computation, of your workload. So typically, sequential or modestly parallel sections of code will run on the CPU, while massively parallel sections of code will run on the GPU. So we're going to have single thread or very few threads of execution running on the serial code, on the host processor, on the CPU, while we are going to have a parallel kernel running on the device, the GPU in this case, utilizing multiple threads, multiple SIMD units and lanes at the same time. When the parallel kernel finishes, control returns to the CPU that may execute more serial code and at some point launch a new parallel kernel onto the device, the GPU, in this example. You will see that writing GPU code, CUDA code, or OpenCL code is not that difficult, but we definitely need to learn how to do it and change the mindset. Here you can see a very simple example of how to port a sequential CPU code that operates on 3 different arrays, 2 input arrays A and B, and writes the result on an array C. In CUDA code, what we do is kind of unrolling this entire loop and assigning one iteration of the loop to one individual thread. We'll have thousands or millions of threads running on the GP inside the GPU at the same time, and each of these threads is going to do relatively fine-grained computation because they are just accessing one element from A, one element from B, adding them and storing the result in the output array C. So as you see, we need to change our mindset when it comes to programming the system. We need to have this parallel computing mindset in order to be able to map the computation onto all these millions or at least thousands of available threads that we have in GPUs and other parallel devices. So hopefully, even though Fisher said that this is hard to do and hard to change, we will learn how to do it, and we will learn how to optimize code for GPUs and other heterogeneous devices as the ones represented in this slide. If you want to check some good examples of parallel programs and heterogeneous execution on CPU, GPU, FPGA, you can take a look at the Chai benchmark suite, for example, that we developed a few years ago with different collaboration patterns for, as I said, these different types of devices, different benchmarks with different types of collaboration patterns, and also different versions of Chai benchmarks in CUDA, OpenCL for CPU, for GPU, for FPGA, and even for simulator. So this is all for today. I am done with my part of the lecture. So guys, if you have any question, please let me know right now. If not, I send you an email sometime later today or this weekend in order to find a good time for everyone for meeting too, so that we can discuss the projects, know what are your main interests, and based on that, sometime next week, we will decide what's the right hands-on project for you.
Will we get a list of the available projects in general beforehand, or will this be a surprise?
We will present that in the meeting.
Okay.
And after that, you will get the list in Moodle.
My main question is, how much time are you going to have in order to work on this project?
So for the course itself, there is one lecture that shouldn't be longer than this one today, basically 1 hour at the most. The amount of time that you are expected to spend on the project is a few hours every week. I think that this is something that you will discuss directly with your supervisors, but a lot in this course as well depends on what is your own excitement and how much you want to learn and how far you want to go. Because if, for example, you work with me on an implementation of a certain algorithm on a GPU, you can just reach the ground by implementing a basic version with some, well optimized or at least reasonably well optimized implementation, or you can play more fancier optimizations, do more design space exploration, and obviously that will require more time, but will also allow you to learn more. So a lot in this course depends on how excited you are and how much you really want to learn and how far you really want to go.
Okay, thank you. And one last question: when is going to be the deadline for these submissions?
There is no deadline. The deadline is just the end of the semester. That we expect that you complete the project by the end of the semester, and after that, someday, probably in late June or July, we'll have a final meeting where you guys will present your different projects. But that also shouldn't be like a very long presentation, maybe just 10-15-minute presentation or so. Okay, thank you for the questions. Anything else? Sounds good. So yeah, if there is nothing else, I think that we are done for today. I really appreciate that you attended, and I hope to see you next week and have good discussions.